So we proved it last time, the PCP theorem. And now that we have obtained constant query complexity, we might ask, how small can the number of queries be, right? So we've seen how to get some constant, okay, that just pops out from this constant is ultimately decided by the innermost PCP, okay? So if you're actually interested to see what is the constant, then you would have to open up the exponential size PCP, count the queries, right? You will get something like 10, 12, roughly like that. And you will get some constant. Your soundness error will also be some constant, probably pretty ugly, right? So something less, a constant less than 1, but if you want to bring it back down to a half, you may have to increase this, okay? So the question that we want to look at today is how small can the number of queries be? How small of a constant? So can we expect 2? Can we expect 2 queries? Actually, let me ask first, can we expect 1 query? So we long time ago, we've seen this, right? So 1 query, no, right? Because that's in P, right? I can just check both possible answers, and I can also go over all randomness, right? So that I can simulate in P. Can I expect 2 queries? So let's take the CSP view. Let's say that I have a verifier and it makes 2 queries to a binary proof and has logarithmic randomness. As a CSP, what is it? Okay. I'm gonna say that we get an instance of 2 set, right? We have a polynomial number of clauses. Each clause will depend on 2 variables. The variables are Boolean. Okay, this is an instance of 2 set. But 2 set is in P, right? So cannot expect. Two queries, okay? However, the algorithm for 2 set makes a very crucial use of the fact that the variables that you are trying to assign are Boolean valued, okay? The same algorithm actually doesn't work when you start moving to higher alphabets, okay? So, and this is consistent with the fact that actually we already know how to achieve 2 queries, okay? We just have to give up on the alphabet and go to a larger alphabet, okay? So we're going to apply something we already know to prove a lemma. Okay, and the lemma is that there exists constants, let's call it S0 and K0, such that NP is in PCP with a soundness error of S0, logarithmic randomness, 2 queries, and K0 bits answers. These are constants, okay? So how do I, again, we've proved this already before. How do I prove that this is the case? Okay? Again, notice that the difference between the 2 set case is that my alphabet size has increased to some constant. So every time I read a variable, I get back a constant number of bits as opposed to 1 bit. How do we go down to 2 queries? Yeah. Yeah, I bundle them up. So basically, I create symbols that encode tuples of queries. In one query, I collect an entire tuple and I run my verifier. But then I don't really know whether this tuple means anything, right? So I'm also going to read off somewhere else where I have one instance of the proof and I check it for consistency. Okay, so we've proved this before. So here we're directly apply the inclusion. PCP CS RQ sigma is contained in PCP C. I don't know about the C here. Let me leave a 1 here. And 1 minus 1 minus S over Q R plus log Q 2 sigma to the Q, right? So this log Q here that comes in has to do with the fact that we're picking one out of the Q queries and we're checking it for consistency, okay? So we're applying the inclusion, this one, to the PCP theorem. Right? So at this point, we have a constant number of queries, so it's okay to take a hit in the soundness error depends on the number of queries because it's a constant. And similarly, now we're taking a hit in the alphabet size that blows it up by a constant, but that's okay as well. Okay? So, all right, but we took a trade-off, right? We reduced the number of queries and our soundness error went way up. Okay? So the question that we can ask is, can we have both small error and number of queries? If you remember, in the week when we discussed hardness of approximation, these were pretty much, given that we always have logarithmic randomness, these were the most important measures of efficiency, okay? So rather than having to trade them off against one another, it would be better to have both of them very good, okay? And now we're a bit in a bind, because if we have 2 queries and crappy soundness error, I want to try to boost it, but that requires me to ask more questions, right? If I ask more questions, then I say, okay, I'm going to go back to 2, but I'm losing my soundness error, right? So it's unclear what to do. Also notice that we did see various ways of improving soundness error. One was just run the verifier independently multiple times. Another one was use an expander so you can save on randomness. Okay? This doesn't help us here, okay? Because the number of queries, we're still asking more queries. It's just that we were sampling them in a randomness efficient way. Okay? So we really have to do something that is like different. So here, the idea is to do a different type of repetition of the verifier. So while just running the verifier multiple times is known as sequential repetition, what we're going to do here is something called parallel repetition. Starting from 2 queries, we'll still ask 2 queries, but we'll enlarge our alphabet further, okay? We'll stash our extra repetitions into a bigger alphabet, okay? So let's first see a picture for 2y's parallel repetition. So my proof is going to be quadratically bigger than before. So if before it had length L, now it has length L squared. Okay? And now in each symbol, I'm going to write a combination of 2 symbols from the prior proof. Okay? So for example, here I'm going to put the first symbol of the proof, and I'll write again the first symbol again. Okay? Now here I'm going to write, say, again the first symbol, but then the second symbol of the proof. Okay, and I do it L times, where now I've written L times the first symbol and all possible symbols of the proof. Okay, now I switch to the second symbol. Okay, by 2 by 2, by 2 by 2, up to pi 2, pi L. Okay, and so on and so forth. I'm just writing all possible pairs of symbols, okay? And now I'm going to have my new proof, called capital Pi, that looks like this. Now, of course, in general, an adversary might fill in these pairs of symbols in whatever ways it wants, right? So if in the first location these two things are supposed to be the same, they don't, I mean, an adversary can just do whatever they want. They can write it down. Similarly, going across, these are supposed to be the same symbols up for the first L locations. Again, an adversary can do whatever they want. Okay? So there could be all kinds of inconsistencies into this L squared size proof. Nonetheless, that's the format. And the test that we would like to run is to say, look, run the verifier on the upper half of the proof, or maybe I should call it big pi, let's say a 1 star, right? It's kind of the first row, x row. And then I'm running v on pi to the second row, okay? With some other randomness, okay? But then, so each of these things is going to produce two queries, right? So it's going to say, I would like to ask Q11 and Q12. So these are the queries of the first run, or maybe let me call it Q row 1, okay? And oh, that's a terrible name. Let me just Q of row will have Q11 and Q12, right? And Q of row prime will have Q21 and Q22, right? So I'm running a two-query verifier twice. I will get two queries here and two queries there, right? Remember that I want to ask two queries, not four, right? So what I'm going to do is I'm going to take, I need to create two symbols, okay? Consisting of two of these each, okay? So I'm going to create from this the query set that consists Q11 on the top and Q21 on the bottom. That's kind of one query to this proof. And the other one is going to be Q21, Q22, right? This is consistent because I'm trying to run this verifier on the top one, right? And indeed, his queries go to the top, right? And his queries go to the bottom, okay? So let me just write it in general how it looks like, okay? But is it clear syntactically that I'm making two queries just over a bigger alphabet, okay? Yeah. All right, let's define Vt to be the t-wise parallel repetition of V. It takes as input a proof that maps from L to the T to sigma to the T, right? So I'm taking a tuple of T elements and I output a tuple of T symbols, okay? I mean, I map T indices to T symbols. Okay? So Okay, can anybody help me fill this in? So at least to make sure that we have we've understood. So I've written the special case when t equals 2. Okay. So what's the first thing that I do? Excuse me?
You have t verifiers.
I have t verifiers, so they each need a random string. Okay, so I'm going to sample row 1 through row t. Okay, so there it is. Then my goal is to make queries, right? So I should figure out what are the query sets of each of these verifiers, right? So deduce the query sets. Now these are going to be, each of these is going to be subsets of 1 through L, right? Because the original verifier wants to query into a proof that has L locations. So each query set is going to be a subset of the integers 1 through L. I have t such subsets. Now I need to construct a well, in general, of course, parallel repetition work syntactically makes sense, not just for when these things are each 2 queries. It can be whatever number, right? Now I need to construct but let's do it for 2 queries because maybe it's easiest. I need to construct the 2 indices, okay? So construct the 2 indices. Now the indices are going to be in L to the t, right? So the first index is going to be really a vector. Okay, so here are our 2 indices into the new proof. How many entries do I expect to have here? T, right? Okay, so what is the first entry here?
First position Q1.
Yeah, so I can write a Q11, so that's first position in the query set Q1. Now here I'm going to put the first position of query set Q2 up to the first position of query set Qt. Okay, so that's my first T tuple. And here I'm going to put the second position of the first query set, the second position of the second query set, up to the second position of the last query set. Right? Now, syntactically, each of these are queries, right, into that proof. So then I'm going to say query a big pi at I and j to get, I will get back answers, right? Now the answers are going to be themselves t-tuples of symbols, right? So let's call them A1, A2, AT. That is one symbol. And this is the other symbol, right?
That makes sense to be Q12, right? Oh, yeah, Q12.
Where, sorry?
Yeah, these two queries should be Q12 to Q2.
These two?
No, that one.
So this is the, I think.
Yeah, another one, second one. Maybe on the right should be Q1, Q9, Q1. Yeah. Right.
Thank you. Yeah. Thank you. Yes. Okay, somebody following. That's great. Wait, so now I've collected back the answers. And remember, sort of my repetition goes this way, but my verifiers are thinking this direction, right? So in the last step, I'm going to check that all decision predicates are happy. So for I going from 1 to t, I'm going to check the decision predicate given x, then AI and BI as the answers and sigma I, so not sigma I, rho I as the randomness, it outputs 1. Right? I'm saying take a decision predicate, give him back the answers for this randomness, and output 1. Okay? Again, the verifiers are thinking in this direction. So again, parallel prediction is really confusing because there are two different directions. One is the way you sort of repeat, and the other one is the direction of the queries. If you have more queries, this is totally fine, right? You just have 3 queries, 4 queries, 5 queries. You still construct more tuples, and obviously if you have more queries to begin with, then after a parallel prediction, you just preserve the number of queries, okay? Okay, so look, syntactically this makes sense. And from a completeness perspective, it also makes sense. An honest prover can clearly take kind of you can think about it, the tensor product of the original proof, right? Whichever many times you are repeating, write it down, and that's a valid proof for the transformed verifier. The only question is whether, as we do this, our soundness error improved. Why? Because we want to improve our soundness error, right? So we have gone down to 2 queries. We are complaining about our soundness error being too high, so we're hoping that by repeating the verifier in this way, that doesn't increase the number of queries, our soundness error would go down. Okay? All right, so really what we would like to show is an inclusion of this sort. We have a PCP, 1S, R, say 2, sigma, is contained in PCP 1S prime, RT, 2 sigma to the T. Right? This is kind of what has happened. And the only question is, who is this guy? How small as a function of T it is going to be? Yeah, how small is it going to be? Do we have any guesses? Yeah?
Can't the prover just put the same elements in the same spot, and you wouldn't get any soundness improvement?
The same elements.
Like
so
pi 1, pi 1, and then like pi 1, pi 1 for every, like.
Are you discussing the honest proof?
No.
Well, but then we are discussing that part, right? So we're discussing security, right?
We're talking about the dishonest prover, right?
Okay, so you're discussing a particular dishonest prover strategy. Okay, and what is the one that you're suggesting?
Instead of like doing pi 1, pi 1, pi 1, pi 2, just do pi 1, pi 1, pi 1, pi 1 for everything. So like anytime you query, you'll get like the same proof as before. But like.
So maybe I can put it in a square, right? So in this direction we have kind of one proof, and in the other direction we have the other proof, right? And here you're supposed to put pi 1, pi 1, pi 1, pi 1, pi 1. Here you're supposed to put pi 2, pi 2, right? Mm-hmm. Up to pi L, pi L. And what is the prover you have in mind doing this in the diagonal?
Yeah, it's going to do that, but it's going to make you always choose those, basically.
I always choose the
pi 1, pi 1.
No, I know. I choose whatever I want.
Yeah, but you don't, like, if you say you choose, like, pi 1, pi, like, n, you don't know.
Yeah, but you see, like, all these things are completely mixed, right? You cannot, I mean, you can try, you can, well, first, rho and rho prime are independent, okay? They're, like, completely independent. So the pairs that you get here will kind of cover everything here, right?
But you're not checking that they're different.
I'm not checking that they're different.
Right.
Yeah.
So I think what might help here is your randomness for the 2 verifiers is different. So even if they get the same answers from the PCP, one might reject even if the other accepts. I think that might answer your question.
Another way to view it is that kind of first, if you take a projection if you project to the experience of any individual verifier, they just see a proof, right? So that you can't do worse than that, right? And then you get more in the sense that you will get better. I mean, you will not get better if and only if whenever one verifier accepts, the other one also does. Okay, and that's a very tall order, and I don't think you can I think it's good to try to play with this with a small sort of PCP example and just do a two-wise thing, you can. And indeed, this is how you should think about it. You should try to think about doing really inconsistent things in the off diagonals, right, and try to prevent things from happening. But this is actually the right approach in a sense that it's really far from obvious that your soundness should go down like nicely. Okay, it's really far from obvious. Okay. Now, now, it is so far from obvious that people actually did conjecture that the right answer is s to the t. Like serious people who conjecture this is the case. And it's actually false, okay, not true. But something almost like it is true, okay? It's a very important theorem due to Ramrazi in 98 or 95, I forget, 98, yeah. That says that when you apply parallel repetition, your soundness will go down exponentially just with a different function. So, and the function, let's call it mu. It's a function that depends on the answer alphabet, okay? Okay, so there is some way to modify s that depends on the answer alphabet, but then once you've done that, it goes down exponentially. Okay? This is called the parallel repetition theorem, okay? And again, the main thing that's happening is that sort of the base of the exponential is something that depends on s and the sigma. Now, the goal of the rest of today and the next lecture will be to discuss this theorem. We'll actually not prove it, we'll just prove a weaker version of it, much weaker. But before we get there, let's maybe try to work out the implications to the question that we asked here. We asked, is it possible to have both small error and number of queries? Okay? So what is it that such type of theorem lets us assert? Can we talk about a sort of two-query PCP theorem with small soundness error? And how do we do that? Like, how small of a soundness error can I expect with two queries? Yeah.
As small as you want, as long as you're willing to pay for the alphabet size?
I mean, this is what it's saying, right? And the point is that we need to convince ourselves of how big, how much we can afford in terms of parallel repetition. In terms of t, how big can I make t?
The amount of randomness.
Well, so we're multiplying. So we're starting with log randomness, right? Now I multiply that by t, right? Our budget is log. So how big can t be? Huh? That would be log squared, right? Because r times t, right? Log times log, that's log squared, right? So we can afford less than that. How much? A constant. Okay, good. So that's the point, right? So clearly parallel repetition says, yeah, you can make soundness smaller if you're willing to pay for it in the alphabet size and the proof size, okay? But once we apply it to the PCP theorem, we need to realize that, yes, we can apply t-wise parallel repetition for any constant t. We cannot go above that, okay? Because when we do, our proof size is going to become super polynomial, okay? We actually don't specifically care too much about this guy becoming super constant, maybe. For some applications we do, but this is really like a problem, okay? In most applications, it would imply NP reduction that is a sort of a super polynomial size. That's not good, okay? So the corollary tells us that we can, for large enough constant alphabet, obtain any soundness error that is as small as we want, okay? With two queries. So here it is. For every epsilon greater than 0, there exists an alphabet that has size that is polynomial in 1 over epsilon, such that NP is contained in PCP 1 epsilon order log n log 1 over epsilon 2 and sigma. Okay? So here the soundness error is as small as we want. This is how much we want it. We're paying some alphabet of that size. Okay? And this is the size of the proof. I mean, this is the 2 to the least will be size of the proof. Okay? All right, and the proof is just that we apply the parallel repetition to this statement here. With t, there is some constant that depends on S0 and K0, and it's a log of 1 over epsilon. Right? All right, this is a pretty sort of direct implication, and it's just telling us that parallel repetition helps us making sure that our soundness error can be arbitrarily small. Okay, that's all we said. Now, any questions so far? Okay, we will discuss this one in a moment. I just want to briefly mention how far one can go in this direction and say, okay, with constant alphabets, really should expect only like constant soundness error. But okay, what if I make my alphabet a little bit bigger than constant, a little bit super constant? Can I expect sub-constant soundness error? That would be nice. Okay, and notice parallel repetition will not get us there. Okay, so kind of other techniques are needed. Okay, so and this touches upon sort of one of the major open problems in the area. Something known as the sliding scale conjecture that quantifies what are believed to be the limits of this play between soundness error and alphabet size when you fix the number of queries to be 2 or a small constant. And so the conjecture says that there exists some constant number of queries, at least 2, such that for any error that you might desire, as long as it is at least 1 over poly, there exists an alphabet, okay, of size related to the error, such that NP has PCPs with soundness error epsilon, again as a function of n, logarithmic randomness, q queries, and the alphabet sigma. Okay? So when epsilon is constant, then we have the answer. But this is called sliding scale conjecture because it's basically saying this is the full range of possible trade-offs. Okay? And the conjecture says that all these trade-offs are possible. Now, you might wonder, why is it that I cannot expect an error that is smaller than 1 over poly? Well, just some brief remarks on why that's the case. Certainly, we always expect epsilon to be at least 2 to the minus r, where r is the randomness. Why would that be? Yeah.
If that wasn't the case, though, I mean, all choices of randomness would make it pass, in which case you're not then NP.
then you're in P, right? So kind of the probability space over which we're working has granularity 1 over 2 to the r, right? So if you have a soundness error that is strictly less than 1 over 2 to the r, then it means that your soundness error is 0, okay? But if your soundness error is 0, then it means that we're back to P, okay? So when your randomness is logarithmic, then it means that this soundness error must be at least 1 over polynomial, okay? Now, also, you would expect epsilon to be at least 1 over a sigma to the q. Why would that be? So what do you think this is indicating? Yeah, so it's going in that direction. So look at a local test that we might be running on a certain choice of randomness. First, that local test should have at least one satisfying assignment. Why are we running it otherwise if it can never be satisfied, right? So every local test that we are running on some randomness must be satisfiable by some choice of Q symbols from sigma. Okay, otherwise we wouldn't be running it. Now consider a random proof. Pick a random proof. A simple expectation argument will show you that this sort of random proof has a sort of non-zero probability of satisfying assignments, okay? And when you kind of de-randomize this random proof, you can show that your soundness error could not have been smaller than 1 over sigma to the q, okay? So I'm not going to do this because today I want to talk about other things, but the point is like these are sort of two ultimate limits, that for a given randomness and a given sigma, your soundness error cannot be smaller than a certain amount, okay? And yeah, since R has been fixed, you have this absolute lower bound of 1 over n, right? And then these two guys need to be related, okay? And here you have O of 1 because Q is a constant. All right. In terms of do we know anything beyond this? The answer is yes. So there is a line of works that is sort of trying to approach a sliding scale conjecture, and the name of the game is basically trying to come up with PCPs where you get subconstant soundness error over alphabets of super constant size. Okay, and those are very nice and also rather difficult constructions. We're not going to discuss them in this course. And this question remains open, and it's a really beautiful problem. Okay, so let's come back to parallel repetition. So my goal for the next, lecture and a half is to first translate this question to the language of games, because typically this question is not studied for PCPs, but it's studied for games. Okay, and then in that language, I want to convey why it's non-trivial. We're going to see an example of a game. If they repeat it twice, it's no harder to win the twice repeated game than it is to win one of the instances. Okay, so as an example, very small, constant size, where actually you can win with the same probability. Okay, nothing changes. Okay, so we have to introduce this notion of two-prover, one-round games, which is what it describes. Okay, so you have a prover 1, a referee or verifier, and a prover P2. And the verifier samples a message from some distribution Q. It sends X to P1, Y to P2, and you get back answers. let's call them, according to some function f and according to some function h, and it will decide according to some predicate. Okay? Now, these two provers are not allowed to communicate in the sense that it's not like when P2 receives Y, he calls up P1 on the phone and says, by the way, what do you get from V? I got Y. And so, oh, I got X, right? So they're in separate rooms, not allowed to talk. They can share randomness in advance if they want, but it doesn't really help them. So I'm not going to get into that. So let's imagine that these two guys are deterministic. So they win the game if they're able to satisfy this predicate. Okay, predicate is a Boolean function. So the value of the game is the maximum probability that any two players can win this game. Okay? So can anybody suggest an expression of how to write it? So the value of the game usually is called omega of g. How can I write, using a mathematical expression, the value of the game? So what do I need to do? What do I need to consider? All possible what? All right, let's say for a fixed f and a fixed h, the probability that they win is the probability that right? So for a fixed f and h, the probability of winning the game is this one, right? That's just how I defined it, right? Now, the value of the game is the maximum probability. So how can I complete this expression to an expression that describes the value of the game? I take what?
The maximum.
Yeah. No. Like so. Again, so for a fixed f and g, this is the probability they win. Okay. The probability they lose is 1 minus this, right? So let's just look at the probability they win. The value of the game is, well, I can just look at all possible f and h. Right? That's it. Okay, I'm just saying there are two provers. Their strategy is the function f and the function h respectively. As I quantify over all possible strategies, this is all they can do. Okay? So the value of the game is the maximum probability of winning. All right. Now, let's just see how parallel repetition is in this language. Let's say that now I'm looking at parallel repetition for this game. How would it look like? Okay. I can obviously run this game sequentially once and twice, right? But parallel repetition means like I'm doing things in parallel. So how would it look like? Yeah.
Leave x1, x2 to p1 and y1, y2 to p2.
Yeah, and where do they come from?
They're both random sample pairs.
Yeah, so I just run two games in parallel. Like imagine that kind of there's one game running here, another game is running here, right? And it's just I'm like running them in a lockstep, right? That's why it's called parallel repetition, because we're going to do it in parallel. So I can sample x1 and y1 from Q, and IID from that I also sample x2 and y2, and then in one go I provide x1 and x2 to P1 and y1 and y2 to P2. Now the answers are in general. P1 is going to say, well, I have a function that is specialized to answer the first game, but this function will receive as input both of them, right? And there's another function that will say, given both questions, let me answer the second game, right? And ditto here. There is a function for answering the first game and a function for answering the second game. But both functions receive the totality of information they have received because they can. And winning the game means that you have to individually win each of those games. Okay, so this is what parallel repetition is. Why are we discussing games? Well, first, there is a bidirectional relationship between two query PCPs and two prover one-round games. I don't want to go through it, it's very boring, okay? You have all the sort of tools you need to see this bidirectional relationship. In the language of games, it's just easier to study parallel repetition. In particular, you see that this picture is a lot more pleasant than this picture here, right? So that's why that's why people study them like this. Now, we haven't introduced this language. Within this language, let's consider a particular game that I want to study. Okay? Oh, by the way, parallel repetition here means what is the value of g to the t versus the value of g to the t, right? Where g to the t means the t-wise parallel repetition of the game. Something that we, of course, know is that this quantity that we're trying to understand is certainly sandwiched between these quantities, okay? As a prover, you can choose to treat each game independently. You can certainly try to win only one game by forgetting all others, and in between there is sort of the quantity we're trying to understand, right? Okay, so let's look at a particular game. Let's remove this ugly thing. So the first counterexample to parallel repetition was actually given by Lance Fortnow in 1989. By counterexample, I mean that the decay is not exactly exponential, but something else, right? So that's actually not the example we're going to see. Uriel Feige gave a very nice example that goes by the name of non-interactive agreement. And the game that we study is the following. So I am going to rename the provers to be P0 and P1, simply because it's just going to be easier to describe this particular game. The verifier samples 2 bits, B0 and B1 IID, and sends B0 to P0 and B1 to P1. Now, both provers are supposed to reply with 2 bits each, U0, V0, U1 and V1, okay? And the predicate checks 2 things. First, that they answer the same thing, namely they agree on, pretty much, they send the same message back to the verifier. And so far, so good. I mean, you could win this game with probability 1 by just answering, hello, all the time, right? We're not using B0 and B1, like in this check. So let's use that. We're going to check that B U0 equals V0. So what does this mean? This is meant to say that P U0 got V0. Okay? So let's say that I'm prover P0, and let's say the provers are trying to win the game. Then they should agree on who they want to talk about. That's U0. Okay? And then both of them should say that one player what bit they got. Okay? All right, so now we're going to look at a simple claim. We're going to prove that the value of this game, let's give a name to this, G tilde, the value of this game is 1/2. Okay? So first, to prove that the value of this game is 1/2, we need to prove that it's at least 1/2. So just give me a strategy that wins with probability at least 50%. So what's a strategy for the players that they can win with probability at least 50%?
Fix the U0 and U and V, which they always the same thing.
I fix U0 to be the same thing, yes. And then the other one doesn't really matter, right? So let's say that P0 answers 0 and say, I don't know, 1. Sorry, not 0 and 1, 0 and B0. So P0 says, I will make a prediction about myself. And the prediction about myself is about B0. P0 has B0, so you can write that. P1 answers 0 and something random, right? Or 1. So it says, I'm going to make a prediction about P0, even though I'm P1, right? And then I just put something random. Again, it doesn't matter. I can also write 0, 1. Okay? With half probability, I'll be fine, right? Why is the value of this game at most a half?
One prover has to guess something with the other prover's bit, which they don't know, and so.
Yeah, that's kind of intuition, right? So you say, first, there is no reason for the two players to ever disagree on which player they're trying to talk about, right? So either they fix player 0 or player 1, or they pick that player using some shared randomness. But there is absolutely no reason, it's irrational, okay, to consider a strategy for which, for some probability, they don't agree on which player they're talking about, because it has nothing to do with B0 or B1, they're just shooting themselves in the foot, okay? So let's say that they're talking about the same player, okay? In that world, one of the two players will be making a guess about the other player whose bit they have nothing about, they know nothing about. So the probability of being correct on that one is 50%, right? Okay, so explanation, okay, blah, okay. All right, so this game, the value of this game has 50%. Okay, now we have to look at the two-wise repetition, and the surprise is going to be that the value of the two-wise repetition is still 50%. Okay? So somehow this is a very small and sort of concrete example that gives you the non-triviality of parallel repetition, so that you can feel it. Okay, so now we're going to have to sample twice 2 bits, right? So let's call them B00 and B01, meaning that I'm using the first bit to denote which execution we're in. And then B10, B11, that's the second execution. Now, which bits should I be sent into P0? Right, so these two, right? So B00 and B10. I'm sending to P1 the other two, so B01 and B11. All right? Now, I'm getting back 4 bits from each prover, right? So I'm going to get back U00, V00, and then U10 and V10, right? That's from one prover. And for the other prover, I'm getting back U01, V01, and U11 and V11, right? Again, the first bit in each case is the execution, the second bit is which player is doing it. So now I need to check that this predicate applied independently to each of the 2 executions is fine. So I'm going to check that U00 V00 equals U01, V01. So I'm checking that these two match, right? I'm also checking that these two match. U10, V10 equals U11, V11. So these are the fact that they're saying the same thing. And then I have to check the predictions. I have to check that B U00 equals make sure I don't mess it up. Yeah, V00. And B U10 equals V10, right? These are two predictions. Okay? Now, the claim is that the value of the two-wise repetition is still a half. Okay, let's do the easy thing first. Let's say y, it's no more than a half. Okay? So why cannot the players win with probability greater than 50%? Yeah, exactly. So we have that sandwich over there. Like, as we repeat the game, it cannot be that the game becomes easier than just one single repetition. Okay? Because winning all repetitions in particular requires you to win a single repetition. Okay? And winning a single repetition, even regardless of the other ones, has a cost, which is 50%. So this is simply because the game is no easier. Now, for the other side, we need a strategy that is better than just playing the previous strategy independently across the two executions, because the previous strategy was giving us 50%. Now, if we play that strategy independently in the two executions, it will win with probability a quarter. Okay? Whereas instead, we have the claim here that we can win probability at least 50%.
The same thing for these B execution 0 and you can set B00 equal B10 and likewise for B01 equal B11.
You want to make these two equal?
Yes.
Yeah, so that makes sense. So the idea is you want to correlate and sort of make these things equal. Not only make them equal, but set one of them to be the correct thing, right? So essentially what we want, so I'm going to write the strategy in a moment, and essentially what we want to do is we want to establish a correlation that when one game wins, the other one also does. Okay? So here's a particular strategy. The prover is gonna answer the following: 0, B00, and then 0, B00. And then here 0, B11, and then 0, B11. Right. Is it clear what I'm writing? So P1 certainly knows B00, so he can write this in both rounds. P0 certainly knows B00, so he can write this in both rounds. P1 certainly knows B11, he's writing this in both rounds. Okay. Now notice that, of course, what's happening here is that they're winning here with probability 50%, right? Because the probability that B11 equals B00 is 50%. Here, the probability that B00 equals B11, sorry, that B11 equals B00 again is 50%, right? So at least the individual winning probabilities for each round are the same, but they certainly win everything whenever B00 equals B11. When that happens, they win both rounds.
Shouldn't it be 1 B00, 1 B11?
Do I need that? But when they equal, doesn't matter, right?
No, because he also has to say the right thing.
Oh yeah, there's a 1 here. Sorry.
Yeah.
Okay. All right, so when you look here, it's saying he's saying the correct thing about himself, and he's right with 50% probability. But they certainly win both rounds whenever b11 equals b00, right? And that happens with probability 50%, because the fact that you get 2 IID bits, the probability that they equal, it's not a quarter, it's half, right? Okay, so that's troubling, right? Let me keep that. So it turns out, so we can leave this as an exercise, that you can win any t-wise repetition, t over 2, okay? How? Well, you just play the same strategy every 2. Okay, so it's maybe not an exercise, I guess, also. And you might wonder whether something more devastating is possible, okay? Because this was just basically saying, okay, I am pairing up these games 2 by 2, but you know, t is a lot, right? T will grow. So now you've lost 2, and maybe you say, okay, fine, I've lost that. Will I lose more? Turns out that for this particular game, you can prove, it's also shown by Feige, that the value of the game is actually exactly this. And one good way to think about it is that, of course, you have your exponential decay, it's just a different constant, which is what we were saying here, right? So, so this game, even though it looks like something fishy is going on, it's actually fine, right? So you can repeat it many times, and it will become harder arbitrarily, and particularly, you know, with this exponential decay. Okay, so even though this looks like bad news, it's only constant size bad news. Asymptotically, things work out. Okay. Are we fine? So then the question is, what happens in general? Okay. And the answer is that it's rather messy. Okay. So the PCP theorem says that in general, you can only play sort of constant size games, or rather, not games. You can only sort of conduct this type of strategies, essentially, with saying that because you still have an exponential dependence, you know, your correlations that can cause some problems only have constant size, okay? Or more precisely, you can only play correlations that are as dangerous as the answer size. In this particular case, the answer is bits, okay? But in general, there is a dependence on the answer size that is actually necessary. So I think I put on the website some links that point to papers where you can actually look at an example where the dependence on sigma shows that the dependence on sigma is necessary. Okay, so this is like understood. Okay. However, you know, to some extent, the most interesting thing, you know, when you see this type of problems, of course, you would like to prove this, but it's a difficult theorem. So what we'll see instead is that we'll show that as t grows, eventually the soundness error must go down. Okay, so that's what we'll prove. Okay, that the limit as t goes to infinity for a game, the soundness error tends to 0. Okay, so this is an analysis type statement. It tells you that eventually things go to 0. It doesn't tell you the rate of decay. Okay, so that was one of the first things that people proved. Okay, before getting here. Okay, so I'm gonna just write down the theorem, and next time we're gonna prove it. So before the parallel repetition theorem, there's a theorem of Verbitsky, Oleg Verbitsky, in what is this, 96, that says that if the original game has values strictly less than 1, then the limit as t goes to infinity of the game, repeated game, is 0. Okay? This is saying no matter what happens, as you repeat the game, it gets harder. Okay, eventually. Okay? This result is of historical importance. First, it was the first general result that said that, so before this, people proved special parallel repetition theorems that said, well, if the game looks like this, then for this class of games, we can actually show it goes to 0, and here's even the rate of decay. Okay? But this was the first time that something general was said. It says for all games, including nasty ones, okay, it goes to 0. And actually, to this day, this theorem is quite important because parallel repetition is explicitly about two provers. And the question of understanding what happens in the rate of decay for all games in any number of provers is actually still open. But the proof techniques that are used inside the Verbitsky's theorem actually apply to any number of players. Okay, so we actually do know that for any number of players, if you repeat the game in parallel enough number of times, the summation error will go to 0. So that some parallel repetition seems to hold for all games. The exact rate of decay and whether it is exponential, it is an open question for number of players greater than 2. Okay? Now, in terms of techniques, the proof of the parallel repetition theorem uses a lot of, curiously, actually, information theory. Okay? So things like divergence. It's very much based in information theory, and we'll see like a little bit of it like next time. This theorem is curiously proved actually with Ramsey theory. Okay, so that would be when you take objects and you scale them up and you make them bigger and bigger. Ramsey theory tells you when organization must ensue. Okay, so when an object is large enough, then you can zoom in small enough pieces, then it must be organized in some way. Okay, so next time we'll actually prove this. We'll just briefly talk a little bit about a fundamental result in Ramsey theory. And we'll just see how to black box apply it. And the connection is really direct. Like the proof is simple. Like once you have the statement, the fact that this is the case is really direct. Okay? So it's actually a very beautiful connection. And it uses like a rather heavy tool. Okay, so the plan for next time was we'll prove this theorem and we'll talk a little bit more about the proof for this one. Okay.